Welcome back to the Explainer. Today we've got a really cool puzzle for you. Picture this, you've got a grid of land, but every single day a flood takes over one more square. So the big question is, what's the absolute last day you can still get from the top edge all the way to the bottom?
Now, this sounds pretty straightforward, right? But finding that exact tipping point, that one final day before it's impossible, well, that takes a really clever bit of thinking.
So here's how we're going to break it down. We'll start with the puzzle itself, then check out the obvious first attempt. After that comes the big twist, the real game changer. We'll grab the right tool for the job, and then put it all together for the final solution.
All right, let's kick things off by making sure we're all on the same page about the problem.
Okay, so here's the setup. You've got this grid, all land to start. But every day, one specific square turns into water. Bam, you can't walk on it anymore. And you can only move in the 4 basic directions, up, down, left, right, as long as you stay on dry land. The goal? Pinpoint the very last day you can still find a path from anywhere on the top row to anywhere on the bottom row.
So, when you first hear this, what's your gut reaction? What's the first way you try to solve it? For most of us, it's the most direct approach you can think of.
You'd probably just simulate the whole thing, right? Day 1, flood a cell. Then you run a search, maybe a DFS or a BFS, to check, hey, is there still a path from top to bottom? If the answer's yes, great. Move on to day 2. Flood the next cell and run that whole search again. You just keep doing this until, poof, the path is gone.
And this is a classic trap. I mean, it works, technically, but think about it. You're searching the entire grid every single day. That is so much wasted effort, and it gets really, really slow, especially with a big grid. There's got to be a better way.
Okay, so going forward in time is inefficient. What's the alternative? Well, what if we did something kind of crazy? What if we just flipped the entire problem on its head?
This right here is the big aha moment. Instead of asking, when does the path finally break, let's ask, when does a path first appear? See the difference? Instead of watching land get destroyed, we're going to watch it get created. And that one little shift in perspective, that's the key to everything. So let's run the movie backwards. We start with the grid being completely underwater. Then, one day at a time, we start turning water cells back into land. The problem is no longer about destruction, it's about creation. We're not looking for when the path breaks, we're looking for the exact moment it forms. And as you'll see, tracking things getting built is way, way easier.
Okay, to pull this off, we need the right tool for the job. And for tracking how all these little islands of land connect up, there's one tool that's absolutely perfect.
It's called Union Find. Sounds a little technical, I know, but don't worry about the name. All it does is keep track of different groups of things. For us, it's going to track which little islands of land are connected to each other. It's super fast at 2 things: merging 2 separate islands into one big one, and checking if 2 cells are part of the same landmass.
The setup is really clever. Of course, every cell in the grid is an element in our Union Find structure. But here's the trick. We're going to create 2 special sort of imaginary nodes. One represents the entire top row, and the other represents the entire bottom row. Trust me, these 2 virtual nodes are the secret sauce.
All right, time to put it all together. We've got our reverse thinking strategy and our super tool, Union Find. Let's see how this all plays out.
So remember, we're going backwards in time. We take the last cell that flooded and poof, it's land again. Now, we look around. Are there any other land cells next to it? If so, we use Union Find to union them, basically saying, hey, you're all part of the same island now. And if that new land cell happens to be in the top row, we connect it to our virtual top node. If it's in the bottom row, we connect it to our virtual bottom node. We're literally building continents from tiny islands.
And here it is, the magic moment. We just keep doing this, adding land, connecting islands, until bam, our virtual top node and our virtual bottom node are suddenly part of the same group. They're connected. That's it, we're done. The very moment that happens, that day is our answer. Because we're going in reverse, the first day they connect is the last day a path actually exists.
And in the actual code, this is beautiful. The check is just one simple question. You ask your Union Find structure, are the top and bottom nodes in the same set? The second it says yes, you know you found the day. You just return that day's number, and you're golden.
So this whole thing isn't just a cool trick. It's also crazy efficient. Think about it. Instead of searching the whole grid over and over, we're just doing a few super fast operations for each cell, one time. This gives us what's called a linear time solution.
All that means is that it's blazingly fast and scales really well, even for huge grids.
If you take away just one sentence from this, let it be this one. It just perfectly sums up the entire elegant logic behind this solution.
So what's the big lesson here? What should you really remember from all this? Honestly, it's not just about grids and floods. There's a much bigger idea about problem solving hiding in here.
And it's this. Sometimes the most brilliant solution isn't about working harder. It's about looking at the problem differently. Just by flipping it backwards and picking the right tool, we turned a slow, clunky problem into something incredibly fast and elegant. So next time you're banging your head against a wall on a problem, just stop and ask yourself, what would this look like if I ran it in reverse? You might just find the answer you're looking for.